Welcome to qnawire.
We're given the following chemical reaction, which is a redox reaction at 25 degrees Celsius, and we're told to use the values in Appendix F to calculate the standard free energy change. In this case, since we don't know what is Appendix F, we're going to have two options. That Appendix F is directly the delta G's of formations of the ions or the redox potentials. So in this case, I'm going to assume that Appendix F is going to contain redox potential, since this is a redox reaction, and then I'm going to tell you how to do it in the case that it is standard free energies of formation. So for this reaction over here, we're going to have an exchange of electrons, since we're going to have two silver plus two electrons that are going to generate two of silver solid as a half reaction, and the other half reaction that is going to be involved is going to be iron as a solid plus that is going to produce, over here, iron 2 plus in aqueous medium plus 2 electrons. So in this case, the redox potential for each of them, remember that the redox potential is going to be an intensive quantity, so the potential, it doesn't matter the amount of silver that we're going to have. In the case for silver plus, the potential is associated to 0.8 electron volts. Sorry, 0.8 volts. Since this is going to be the reduction. Okay. In the case of iron, we're going to have the oxidation reaction. So the potential is going to correspond to minus the redox potential. So for the exchange for iron 2 plus to iron as a solid, the potential would be 0.45. Well, minus 0.45 volts over here. So the overall value is going to be, for the whole reaction, E standard for the reaction would be equal to 1.25 volts. Now, we're going to employ the fact that the delta G standard is going to be equal to minus N times Faraday's constant times the E0 potential. The value for N is going to be equal to 2, since we have exchanged 2 electrons on our reaction, so this would be minus 2 times Faraday's constant, which is going to be equal to 96,500 coulombs per mole, times the potential, which is 1.25 volts. So over here, the value would correspond to minus 241,250 joules, or minus 241.250 kilojoules. So over here, I employed a rounded up value for Faraday's constant. So if you take the full value of F, you're going to get the answer over here of minus 240.556 kilojoules per mole. Or maybe if the values for the standard potentials are different from the ones appearing on your appendix. I use the ones on the book that I use, so there is a potential difference there. Now, in the case that the values on the table are going to be delta G's of formation, in this case, the delta G for the reaction would be equal to delta G of formation of iron 2 plus in aqueous medium plus 2 times the delta G of formation of silver as a solid minus 2 times the delta G of formation of silver plus in aqueous medium minus the delta G of formation of iron as a solid. And with that, it would be all. Thank you very much and have a good one. In this case, I think that the most probable scenario is going to be that this is the correct approach, since I suspect that the Appendix F is probably redox potentials. So with that, it would be all. Thank you very much and have a good one.